work come in?
Okay. So I made this title a question mark because most of what I'll be talking about are questions. And I would like, so actually I have not worked in differential equations or anything to do with dynamics. So my work is primarily about statics. Of course, there's still differential equations there, but and my goal most of the time, I'm a discrete geometer and a complexity theorist. And my goal is to see whether you can look at an algebraic problem, for example, or a constraint system and reduce it to at least answer some of the interesting questions using purely combinatorics, using the graph, the underlying graph. So at least in a generic situation. So my interest in, I wasn't sure, frankly, I have to say, I wasn't sure what to talk about, right? Because I'm not familiar with your community at all. You're not one of the communities that I normally associate with. There are 3 or 4 other, about 4 to 5 other communities that I talk to, but so anyway, I wasn't sure what to talk about. So looking at some of the talks and some of the papers that were there, I made this up. So essentially, the way I think about my approach to, for example, materials modeling would be to view the current state of the art in this fashion, and then see what is it that I am doing that is different, So first of all, before that, I wanted to say it's some of this work, not all of it, some of it is joined with a collaborator, Jörg Peters, who is also in the computer science department. And we had a joint DARPA grant together, which is from 2017 till the end of this year. And we basically, that's the only place, that's the first place that I was exposed to the idea of materials modeling. Before that, I was doing other stuff. I'll tell you as we go by. So, so essentially the way I understood it during these 3 years of my education of the use of, microstructural design and so forth, I saw that the way people approached the problem was roughly in this way. So you have a kind of, obviously things are made up of stochastic distributed kind of material. So if you look at a block of concrete, for example, or you look at, a carbon fiber composite or something of that nature, essentially you have a there's an underlying discrete structure. If you go even further down, you may be looking at molecules, or if you're looking at soft matter, you're looking at particles. So essentially there is a discrete underlying structure, which is typically written using pairwise interactions between the particles or molecules or fibers or whatever it is that you want to think about. So there's an underlying microstructure, and there's physics there. There's, depending on what you're studying, and these days this idea of multiphysics is very popular, in the sense you're simultaneously studying, I don't know, maybe, mass at the same time, sort of optimizing mass while having certain constraints on stresses or electrostatic stresses, or, maximum electric field, simultaneously looking at thermal, electrostatic, magnetostatic, stresses and all that together. And you're trying to design maybe the microstructure that satisfies certain constraints and at the same time fits certain external form. So there's a macro shape. And then you're optimizing something and you're constraining something. So you maybe say want the lightest, you're optimizing mass and you're trying to ensure that stresses are not too high or some, depending on what the physical constraints you're looking at. So you have sort of a discrete structure underneath. Then typically you make it, you take these whatever conservation laws that you have at the discrete level, and you sort of make a continuum mechanics model. And so typically you have a homogenized bulk properties that you extract, sort of like a representative volume element or something of that nature from the underlying discrete structure. And you get a homogenized bulk material property right down in a PDE or whatever. And then you have a PDE constrained optimization problem. So as I pointed out, the standard topology optimization, which is a big area. Maybe I wasn't able to listen to some of the talks yesterday, but maybe there were some talks there where you're trying to, let's say, get the lightest possible shape that has a certain stress response, minimum stress response. So, so what you do that is that you use a numerical method to solve, and the numerical method will typically also use finite elements or something. So you rediscretize the domain but using some other finite elements. So those may be unrelated to the original discretization that you started out with. And then you solve it in this space, and then you go back and say, okay, now I have solved this PDE, and now let me try. So typically the topological optimization problems will tell you where the mass has to be, where, are solving for the mass distribution, given some given some constraints on, say, electrostatic stresses or mechanical stresses or whatever. So they have tell you the mass distribution at a microstructural level, and now you have to sort of maybe adjust it to the underlying microstructure somehow. And this last physical consistency between the thing that you solve for, your solution, with the underlying microstructure may often involve certain adjustments and approximations, which is a post-processing step. So so the goal, in a way, of this discrete geometric analysis, as there's a paper by two Japanese, I forget, and so they've written several papers, is to sort of try to go back to sort of maybe a Platonic, if you will, way of thinking about things, and just directly do computations on the underlying discrete structure, if it is possible. So the goal is to use maybe do it in an approximate way, but extremely fast. And then if in those places that you need to have finer, more accurate solutions, you then go and try the other methods. So so the goal is to sort of build the properties into the representation of the underlying discrete structure. So for example, so if you're trying to do topology optimization, often you will see that people, they write a continuum mechanics formulation, and then when they're solving it using a PDE and doing a discretization, the solution will, even to ensure that the solution is connected, so that the mass distribution sort of, it's ones and zeros here and there in these discrete cells, to make sure that it's connected, becomes a nonlinear constraint, and which is not good. You would like to have linear constraints and maybe an optimization problem that's a function that's nonlinear. But so even connectivity becomes a nonlinear constraint. If you want to additionally ensure rigidity or something, and that the whole thing doesn't collapse, the final mass distribution that you've created, that might require more complicated nonlinear constraints. So essentially, the goal is to have a representation, underlying representation, discrete representation here, that already builds in some of these properties. For example, that it's guaranteed to be minimally rigid, and so the goal is to sort of think of this discrete representation as a potential approach that can work along with some of the classical methods that are being used for topology optimization and so forth. So anyway, this is the program. So the key thing here is geometric constraints. So by the way, I have to say all the pictures that you will see, the talk is going to be a lot of pictures and almost no mathematical formulae, right? Because I didn't know what to talk about, because I'm not, if I start going off in some direction that is of no interest to people, at the very least, there are some nice pictures involved, so there's going to be a lot of pictures. I hope there are lots of questions. If people, you're okay if you ask me a question like, what the heck are you talking about? Why are you saying this? Right? That's fine with me. I'll try to answer that. So so essentially, the underlying structure is a geometric constraint system. That's what I think about it as, this underlying discrete structure. And we've used it for a lot of different things. So we've used geometric constraint systems for designing microstructure, for modeling. I mean, designing microstructure. These days, you can design microstructure in two different ways. One is sort of like the, you're mixing, let's say, you're mixing stuff, with making a composite. You can sort of decide how much of this and how much of that, and what ratios and what randomization is involved and so forth. So that way you can make a microstructure, but you can actually even engineer microstructures these days, and design them to the point where you actually engineer them. Because of 3D printing, you're able to do that. So there's pretty accurate 3D printing. So designing a microstructure in two different ways, and modeling microstructure. So like I said, there's pretty much naturally occurring, natural looking microstructure that you may just need to know how it behaves. So in both of those scenarios, we have used geometric constraints. And the key sort of thing that we've used there is, one tool that's commonly used in terms of ensuring a built-in property is this idea of combinatorial rigidity, which is purely based on the graph, right? The graph of constraints between the constraint system, the graph of the constraint system. So, so geometric constraint system by itself is a polynomial system, typically, because the constraints are written as polynomial expressions being asserted to be equal to 0, where the variables in the polynomials are often positions of the elements involved in the discrete representation, or they could be other things. I mean, they could some parameter that describes the elements. It could be positions along with some other properties, mass or other things. So the second, and so these are all different application domains in which we have used geometric constraint systems, and primarily I'm going to be talking about this first part here, the designing microstructure. Okay, so there are multiple types of geometric constraint systems. There's a huge, by the way, I edited a handbook recently, 600 something pages. It's in Taylor and Francis. It's called Handbook of Geometric Constraint Systems Principles. And all the sort of active researchers in the area of combinatorial rigidity, geometric constraint system solving. So it's a branch of real algebraic geometry, and people in automated geometry inference, which is also uses polynomial algebra. So those people are also there, automated deduction and geometry. So there's like 3 groups of people, researchers who have written those 25 or so chapters. So one of the things is that there are multiple types of geometric constraint systems. So some of the examples I've given here. So the elements here, for example, are the what are called rigid bodies, if you will. And again, this can live in any dimension and doesn't even have to be Euclidean. You will see that there's different geometries are of interest, projective geometry, lots of non-Euclidean geometries are of interest, but at least the pictures here are primarily talking about Euclidean. So essentially you have, bodies, and then when two bodies are sort of incident on a pin, for example, that's what this picture here shows. And there is an underlying graph or a hypergraph sometimes. So similar in here, you have this idea of a body and a bar. So these A, B, C, D, etc. bodies, and you can have sort of just bars between them where it's you sort of assume that the bars are the placement of the endpoints of the bars. Placement of the endpoints of the bars are somehow generic and don't cause any dependencies just from the placements. You have another sort of example would be a pin, what's called a pinned line or pinned subspace kind of systems. Believe it or not, we actually have used these for in machine learning as a model to understand an area called a problem called dictionary learning. So essentially you have subspaces. Here I've just drawn lines as subspaces, and you have, these points are sort of incident points where a bunch of subspaces are incident. And then in addition, you have certain constraints that the subspaces are forced to contain other points, right? So in the dictionary learning setting, we had, these points are sort of like the sample points that you're trying to represent as a sparse combination using dictionary vectors. And so these guys that you're trying to find are the dictionary vectors, and these other ones are the sample points that are given. So you can express all kinds of things using, finite geometric constraint systems, and solving them would then give you the solution. Here's another example of we have used geometric constraint systems to model collagen fibers. Have this idea, you have the idea that you have fibers, and the constraints between them are because they are what are called cross-linked. So cross-linked fibers are very common and naturally occurring, like cells and so forth. The cross-linking ensures that they are incident on each other, but they can slide across each other, right? So they can slide one with respect to the other. They're just incident on each other. So that's another type of constraint system. And then which you can use the pinned line incidence constraint systems to represent that. And then, you just have packed spheres. That's another geometric constraint system where the elements are now points along with, depending on what the constraints are, you could also have the radius of the sphere as one of the variables that represent an element. So it could be the coordinates of the center plus the radius, or the radius could be fixed and you just have the coordinates. And then the distances between so this is used in circle packing. There's a whole area on sphere packing and circle packing where you can sort of, and jamming, where there's an underlying constraint system, geometric constraint system of this type. And then, there are other types of constraint systems, which I won't go into. So these pictures are all sort of
a question, since you suggested to ask right away.
Yeah.
So this goal against, and my question is probably about projective geometries that you mentioned.
Yeah.
Do you find that in goal against, or is it of relevance to goal against anyhow?
Is it of relevance to
goal against, to the materials D, to the D, item D in your slide?
Item D, collagens. Yes.
It's called collagens.
Yeah, collagens. Yeah. It depending on what you want to do. So for how you want. So there's a trivial group. So in other words, you have a certain what is it that you want to studying. So if the group, if you don't care about, for example, any project. So if your invariants that for your space are the projective invariants, then you can think of this geometric constraint system projectively. But in this situation, you may actually care about more than, your trivial group may not be just the project, may not be the entire projective group. You may, for example, actually have a position fixed in Euclidean space. So in other words, if distances are given, for example, so in this example, in the collagen case, these fibers are actually tied to something. So there are fixed positions in Euclidean space that they are actually sitting in. So in this picture here, for example, these white dots are actually fixed points on sitting in Euclidean space. So in other words, the pairwise distances between them is fixed, right? So if that was the application, then you don't want to look at projective space. Then the natural space to be looking at is just Euclidean space.
Sorry, if the distances are fixed, or if coordinates of nodes are fixed?
The coordinates of the nodes are these coordinates are the ones that you're trying to figure out. So you're trying to solve the system and find a solution.
Okay, so if distances are fixed, then you don't consider that in projective geometry.
Yeah, we don't. Yeah.
Okay.
So if these distances are all fixed, then we just use Euclidean geometry for that. But there are other applications where, like in the body bar, there is no, these white points don't exist, for example. Then all you have is incidences, lines and incidences. Then you just have incidence, an incidence system, right? So then projective geometry is the right thing to look at. You want to think of it as, projective geometry constraint system. So, okay. So these are, so the goal, as I mentioned, is, to create sort of with interesting shape constraints, external shape constraints, plus some other constraints, I don't know, maximum stress, minimum stress, whatever. You want to create the microstructure that conforms to that, right? So, and it minimizes something like mass, for example. So you want to minimize mass, you have some constraints on loading, and so they're going to be loading from here or there, and so you have a certain material, so you don't want to, on any member within the microstructure, you don't want too much of a stress, but you also have some sort of external shape constraints. You want it smooth in certain ways, so to simultaneously deal with all of this, we want a design space of microstructure that allows you to do certain basic design operations that are easy to do, that you can, by doing these operations, you can essentially traverse the entire space, design space, and you have certain properties that are maintained. Minimal rigidity never is always there, and you can put things together, you can join things, you can decompose things, and you can design this in such a way that you satisfy the constraint. So, and then on top of this, then you can use your favorite solver. I'll come to that. So this becomes convenient to start using splines or other things to make it get a free form deformation, or make this continuous in a way, and then use methods, that more sophisticated methods for solving PDEs, and that don't rely on the standard kind of finite elements. Okay, so so essentially this is the this is just the goal. The goal is to have a rich, versatile, adjustable, scale independent microstructure representation with built-in minimal rigidity. So the goal is, okay, so you have some external shape that somebody gives you, and they have some constraints. you should be able to decompose it somehow into pieces. The standard kind of, whoops, what happened? The standard kind of partition into regions, mesotetrahedralization or whatever it is, that's what they do usually. And you should be able to look at each one of these small mesoregions, fill it in with some microstructure, have some irregularities, allow irregularities, built-in irregularities in case you want to model naturally occurring microstructure, or use those irregularities to create some holes if you want it, and in order to minimize mass, and then be able to sew these things together. So each one of these small area volumes, you fill in microstructure, and you should be able to sew them together, sort of, and then be able to print it. So in other words, if you have this incredibly huge microstructure, to actually print it, slice it and print it, you need some reasonable ability to store. If you have some million by million by million pieces here, you can't print it unless you have some interesting algorithm, intelligent algorithm, to actually be able to do that. And then you need to, like I said, have a continuous map. So you'll see that we'll have a composition of maps, both one for the free-form deformation that gives you the external shape, and also for the members themselves, of the discrete microstructure, to sort of smooth them out and do use whatever physical representation you need. So that's the overall what we do. So the advantage, another advantages I just want to repeat of this abstract kind of geometric constraint representation, is that the same graph can be used essentially to represent all kinds of different things. And in fact, the constraint, the combinatorial rigidity properties may also be unchanged. Sometimes they're not. I mean, you have to do different analyses, but often very vastly different looking, different physical physical realizations may underlying geometric constraint system may look very similar. And this is just showing sort of different. This shouldn't be here, actually. This last, ignore this thing. This is just how we can attach continuous splines, G1 splines, to take your discrete microstructure and make it into some whatever shape you want. So so we're using this particular underlying microstructure called corner sharing tetrahedra, which are guaranteed to be minimally rigid once we have a boundary stiffening process, which I'll tell you about in a little later. You can use, it's versatile in the sense that you can use it for all kinds of different physical realizations, and the underlying rigidity analysis is the same, doesn't change, of the graph, I mean. Then you can also use it for not just for usual stresses. You can use it for electrostatic, all kinds of things that essentially look like a Laplacian or Poisson with the Neumann or Dirichlet boundary condition. So essentially you can use the same thing. It's just sort of cryptomorphic. You can apply, you can do the rigidity analysis the same way. You can do the PDE analysis the same way, and so forth. So the key theorem, which is called which is the one direction, is proved by Maxwell in the 19th century, and the other direction we only know for d equals 2 in dimension 2 was proved by Hilda Geiringer in 1928, and then, but unfortunately nobody knew that she had proved it, and so everybody calls it Lamant's theorem, and Lamant did it more than 50 years later, or 40 years later. So essentially it says that if you have a graph and the rigidity means that we're thinking about the graph as the vertices as points and the edges as fixed distances. And we want to ensure that the possible positions of the set of points that's that modulo the Euclidean group. Of course, you don't care about rotations and translations of the whole thing. Modulo the Euclidean group, we want the possible positions of the points to be locally unique. So the solution to this quadratic system that says that all the pairwise distances are fixed, pairwise distances corresponding to the edges are fixed, edges of the graph, results in a locally unique solution. So that modulo the Euclidean group. So the question is, if you have a certain number of edges for every subgraph, so this is basically saying that for every subgraph you have some bound on the number of edges, and that ensures that not all the edges are end up in one corner or something, sort of equally relatively well distributed set of edges, and the total number of edges is about that, then this is a necessary condition for rigidity. So rigidity means this local uniqueness of the solution. So Maxwell essentially proved this. I mean, this is very simple. It requires generic in the generic situation. So it says generically independent. You can take your quadratic system and take the Jacobian, and the Jacobian gives this rigidity matrix, and you can show that the rank of the matrix essentially, I mean, having maximal rank or full rank, no dependent edges, and a certain minimum number of edges. Edges are the rows of this matrix. If you, matrix is simply the Jacobian of the distance map. Distance map being from the points, from the vector of points to the edge, pairwise edge distances. So the Jacobian of that map, if it has full rank, then essentially you have local rigidity. And that's just saying that the, you know, it's implicit function theorem or something like that. That's all that it takes. And so essentially that direction is straightforward. The other direction is sufficiency, which is to show that if these conditions are hold, then in fact you have a locally unique solution, or rigidity in that case. To show that, we only know that this is true for d equals 2. And for d equals 3, as stated, the theorem is actually false, and the classical, what is called the 2 banana counterexample, is a very simple example. So this has the right number of edges for d equals 3. So L here, by the way, LC is what is basically just the order of the Euclidean group. So in this case, for D, this will be D plus 1 choose 2, essentially. So that's all the number of rotations and translations in D dimensions. Yeah. So this is D plus 1 choose 2. And for other, you know, slightly different geometric constraint systems, this may be a somewhat different number depending on the trivial motions. But for the Euclidean case, this is D plus 1 choose 2. So for D equals 3, this would be 6. There are 6 rotations and translations in 3 dimensions. And for 2 dimensions, this would be 3. LC would be 3. So here, by the numbers, you know, D equals 3 and LC equals 6. That's 3V minus 6. This has exactly 3V minus 6 edges. No subgraph has more than 3V minus 6 edges. If the sufficiency condition held, then this would be rigid, but it's obviously not rigid because you can move these 2 bananas, so to speak, out of the plane, right? So they can rotate. I mean, they can, about this axis, you can sort of flex them closer to each other or outside. So you can, you know, you have something like this, you can do this, you know. So essentially, so now, however, for our collection, our particular corner sharing tetrahedral structures, we can use a slightly different theorem, which is essentially showing that this simple count actually works. Okay. So as a result, this Maxwell's theorem sufficiency also holds. I mean, I haven't given you the full theorem yet. Full structure yet. I haven't told you how I stiffen the boundary of it. This shows a boundary stiffened structure kind of, but there is a scheme for doing it, as a result of which we actually get so I just realized that because I have this other bar, I didn't see that I actually had the rigidity matrix here on the right side here. So this rigidity matrix actually shows the Jacobian of the distance map. So the map is from the points to the vector of pairwise distances for each one of the edges, right? So that's the map. And so the Jacobian of that map, essentially this matrix, you can see that, for every edge, there is a row, because that's the range. And each row essentially just has for the particular points that correspond to those, that are at the endpoints of those edges, you have P1 minus Pi minus Pj and Pj minus Pi in the corresponding columns, where the columns are the points, So that's basically the Jacobian, and the rank of this matrix is what determines generically whether the structure is rigid or not. So one of the reasons we chose this this corner sharing tetrahedral structure is, these are known to be, mechanical engineers have done a ton of experiments. It's called the Kagome lattice. I've done a ton of experiments. I mean, if you look at the periodic version of this, I'm showing you finite pieces of this, but if you look at the periodic version of this corner sharing tetrahedral structures, they have actually shown that it's called a Kagome lattice, 3D Kagome lattice, and they've shown that exceedingly strong, very strong, in terms of for the mass. So in other words, with the minimum number of members, given this number of bars for the same number of joints, they're much stronger than what's called the octet truss, which is the more commonly used one. So this is just a picture showing, just showing these corner sharing tetrahedral structures. And this guy called Fleck is a kind of an evangelist for these. He's in Cambridge, is a mechanical engineer. He's Hutchinson and Fleck. These are evangelists for this Kagome lattices. Okay. This is the boundaries, that stiffening that I was talking about. Obviously, if I just have the corner sharing tetrahedral structure without the boundary stiffening, it'll fall apart, as you can see. You have to hold it together from the around for it to actually be rigid, otherwise it'll just collapse. So these boundary stiffening is a particular algorithm that we have that ensures the right numbers and ensures that Maxwell's theorem sufficiency direction also holds. So we have this algorithm that basically tells you how to stiffen the boundaries of this corner sharing tetrahedral structure as the size increases. Then come the other operations, and I'm just quickly going to go through these operations very fast. So, you want to be able to add irregularities in order to model, let's say, concrete or something. And what we do is, I heard somebody talk about the Stone-Wales defect. So it's very similar to the Stone-Wales defect. So essentially, you have a type of a dual structure to the original sort of a ordinary triangular lattice. You just create this structure by putting points at the centers and putting triangles here and throwing out the black ones. So that's how you get this. And if you do a flip, what is called a triangular flip, which is a very well-studied thing going back to the 20s, a guy called Wagner started studying them, how you can get from one triangulation to another triangulation using flips. When this flip, once you make this flip, the corresponding structure is here. It's also called sometimes a stone whales defect. And we have a corresponding version of that for 3 dimensions. These are corner sharing triangular structures in 2D, and we have corresponding corner sharing tetrahedral structures. And that, oops, somehow my laptop is extremely sensitive. When I touch it, it just jumps. So that allows us to make these irregularities and it's a random process that allows us to actually talk about the distribution of structures eventually after we apply this process multiple times. Okay. And and the other thing is the ability to sort of prove that you can reach every structure that satisfies certain basic properties using this simple operation. So this is again stone whales. I don't know why it's there again. And then there is this angle issue. If you think of stresses here, you don't want to have a scenario where I don't know what happened to that picture. Somehow that picture has disappeared. I used to have a picture here on the left. So if you have a situation where you have this type of a situation where, obviously all the stresses, they're all compressive stresses, for example, if this were representing touching spheres, each edge is an incidence between a pair of spheres, and then the only kind of stresses they can take is compressive because they're touching spheres. They can't take tensile stress. So then all the stresses are positive. So a vertex like this cannot exist. If all the stresses are positive, the stress balance equation will fail here. So you need to sort of change the angles a little bit, and there's a process of balancing that allows you to change the angle, so you'll get this kind of a more appropriate structure. And this is just applying that process multiple times, and you get these irregular things with whose distribution. The distribution over these structures is something that's it comes through. Oh, now suddenly I got that. Okay, so here's the this is the bad kind of situation which you balance out to get this. Okay. So so you can do this, and sort of refinement of these structures is another operation, and together with the flips and the refinements, you can with some probability you do this, with some other probability you do this, and with some probability you create the flip. So you actually have a process, a kind of a process by which you can understand what the distribution of the material across all different structures that you get at the end, and that allows you, having a handle on the distribution allows you to do sort of representative volume elements for a stochastic structure easier. Okay, so that's the 3-dimensional version of the refinement. I don't want to go into that. And finally, we, there's the ability to sort of glue together structures simply because, we know the positions of this endpoints, and so that allows you to sort of glue together structures and ensure minimal rigidity. So so all these operations together allow you to sort of, and then finally, of course, you can do a free-form deformation of the whole thing. So there's a map, and then you can add, decorate your discrete structure by adding some G1 splines or something like this. So so you have a composition of maps, and you can do this. So yeah, so that's all it is. So I'm looking for something. Here. Okay, so the pipeline for a design operation would be, okay, suppose you want to make a helmet. You have a rough idea what the helmet looks like, not an exact idea, but rough shape constraints. So you just take that and split it up into subdomains. Optionally, you can foliate this these guys so that you do it using 2D structures, if you will, but you don't have to do that. it gets decomposed in some way, and then you create these for each of the pieces. You can put your whole repertoire of possible structures that you can create. You can choose what you want to do when you solve your PDE and want to minimize your stresses and so forth. So that's the overall, this just showing all the different different physical realizations of the same thing. Okay, so now going to the stress analysis, again, on the discrete structure, you can do stress analysis really fast. You have the rigidity matrix, the sort of the left kernel of the rigidity matrix gives you the stresses, essentially. So you can take a vector of a vector S, let's say S times the rigidity matrix equals 0 would give you what is called the self stress. Yeah.
Meera, so now your links are springs?
In this case, I'm thinking of the links as just bars.
Bars, but they're elastic?
No.
No, they're rigid.
They're rigid.
Rigid.
So
it's
far,
like,
they're rigid. Yeah.
That's like reactions.
Yeah.
I see.
Yeah. So, but if I don't make this 0, if I force the stresses to be positive, for example, non-negative, right? So then I can use this for that's sort of equivalent of saying that I have a tensegrity. So which means that I have bars which can only take compression. Those are called struts usually. And then there is other strings, the ties they call them, that can only take elongation, right?
Wow. So it means that you have a kind of plastic springs with no elasticity zone.
Yeah.
Okay.
So they can take compression. So like what they call struts and ties. Ties means they can take a stress, positive stress, and the other ones can only take a negative stress. So what depending on what the members are, you can force, you have an extra constraint on the vector, stress vector, as certain entries have to be non-negative and certain entries have to be negative, whatever. And then your kernel, along with those extra inequalities, will give you the self stress. Now, of course, you don't need, if you have an external loading, you just add that on. So basically you have, F, which is the force vector, plus this omega, which is the stress vector, times R should be equal to 0. So, any force that has an end Euclidean motion, causes a rotation or a translation, cannot be resisted. So the only forces that you have are the ones that are, the only forces that could possibly satisfy this equation would be ones that are don't have any Euclidean component to them at all, right? So so this is this is sort of simple graph-based rigidity stress analysis, and you can use this to do a very quick, you can have a huge microstructure. It can be quite large, and especially if it has this recursive hierarchical structure like we build. The block, the rigidity matrix has a block structure, sort of a hierarchical block structure. So if you're going to solve for the stresses, it's very, very fast, extremely fast, because there's no bending or anything. There's just stress along the direction of the bar. That's it. So so we do a very fast thing, and so we compared it with the people who actually made it into bars and did FEM and finite element analysis, stress analysis. And this right hand side is just us doing our quick quick and dirty rigidity matrix stress analysis. And yes.
So if you have that kind of plastic springs without elasticity zones, how then your structure remains rigid?
No, this is for bars. So when you asked me that other question where I said, if I had extra inequality constraints on the
inequality constraint.
Inequality. Now I don't have that. If I don't have inequality constraints, I allow any bar to be either compressive or tensile, then it's actually a bar. It's like a fixed length bar, right? And then essentially you have, these are all stiff, if you will. They're by the way, the rigidity matrix and the stiffness matrix have the same kernel. I mean, they have the same kernel essentially. So you can use potentially the stiffness matrix. They have the same eigenspace in a way. So this is another comparison, not this time, not with FEM, but with a different structure. So instead of mechanical engineers, like structural engineers, they use this old-fashioned method, which they call trusses. And so this is a comparison with that truss, and that's almost exactly the same. It takes maybe a little bit, it goes a little slower than ours, but we get pretty similar results. Okay, so now comes the idea of how you use the continuous maps to actually solve some PDEs, on these. So by the way, computing mass and all this, there is my colleague who does splines and all that. So they can attach splines to these discrete elements, so to the so that you can compute volumes, Gauss's law and stuff, to just compute volumes exactly of this microstructure. Mass and volume can be exactly computed, easy, immediate, right? So once you attach the splines to them. So anyway, this was a helmet situation where we put the microstructure in there. I don't know if you can see it. It's in here. And sort of had a it's a composition of maps, and I'll show you another picture later. And with the splines, they can actually do, instead of using finite element, they can just do directly on the entire surface. You just compute the heat equation. Of course, heat equation is simple, but we have also done others. So this is what I mentioned by this composition of maps. So you can have, a microstructure inside a microstructure, sort of, and then the whole thing with the free-form deformation. So these maps, you sort of compose the map going from the discrete structure to the free-form deformation, and then another map that actually gives you from the deformed structure to your spline that gets attached to it, like this. So so anyway, I think I'm almost, so here are some other examples of solutions, Navier-Stokes and Cohen-Hillard or whatever, directly solved on these splines without using, and this is another one that we did. This is standard electrostatic, it's a capacitor that we had to compute the, again, was given some constraints like maximum. So there's a dielectric. So we had to sort of get a distribution of the dielectric in such a way that would ensure that the maximum electrostatic field is below a certain number, and the voltage is given, and you had to sort of distribute the dielectric in a certain way so that the stress is minimized. At the same time, the total volume and total mass of this whole object is not too much. So you're given certain properties of the dielectric, such as mass and volume and so forth. And so you want to compress, you want to make a very small, compact capacitor that can take a very high voltage without failure. So essentially, now the microstructure comes in, because if you want to minimize the size of this thing or minimize the mass of this thing, you want to actually have the dielectric not be like a solid thing if possible. So so that's what we did, again, using this technique. So I think I have to go a little bit fast here. Getting deeper into this is a little harder to do now. The other thing we did was, be able to, as I said, to take an arbitrary slice of this curved microstructure. You know, when you take a slice of a curved structure to which you have applied this map, you know, free-form deformation, and then now you have to print it, which means you're taking a slice of that. So there's a way to actually go back here, pull back the map, pull back here, and then now you have a curved slice. Here you have a curved slice here instead of a straight slice here, you have a curved slice here. And then how do you compute the slice very quickly? That's another thing we did. And this is a movie, which I don't want to get into, which actually shows the printing process. This is something that we actually printed. And another important thing, okay, hopefully this will draw some connection to what you talked about, which we chatted about. So if you had something like this, if you doing a free-form deformation is not straightforward because you have to maintain the constraints. If you have particles, you have to ensure that the distances between the pairs is maintained. So you have to maintain those constraints. So you just making a free-form deformation and not doing anything is not going to work. So you have to compute the positions. And so that's where this idea of that I was talking to you about Oleg comes in. So when I saw your talk and Hosean's talk, and I think Hosean mentioned that Ivan also, I saw graphs that looked like this. And you had springs instead of edges, right? These are called series parallel graphs. And what that means is these are graphs that have no underlying K4 as a minor. So these graphs have a very special property that if you, okay, where are these graphs used? I'll come to this later maybe. Yeah. Okay, so if I took, for example, one such graph, this is a very simple example of such a graph, just a cycle. And instead of saying one, think of this as a distance interval. So in other words, between these bold bars are, they're not quite bars, they have a minimum value they can take of their length and the maximum value that they can take of their length, right? So there's a distance interval constraint between that is represented by these bold lines. And now I want to, and these points are living in 2 dimensions, right? So I want to know all the possible positions that these points can take, of course, modulo the Euclidean group, while ensuring that the distances are within that interval, right? And so in order to, usually this thing can look, if you just think of the Cartesian coordinate system here, so it's a one-dimensional, it's a 2-dimensional Cartesian space, and that can look extremely ugly. So if you try to represent the coordinate space, I don't know if you've seen these linkage, you know, linkage configuration space results, and those can look extremely ugly. They're disconnected and they wrap into each other and whatnot. And now the goal is to sort of try to traverse this space, sort of walk this space. And the way we do this is by taking, these have to be judiciously chosen, but there exists a pair, some set of non-edges. In this case, we check this pair. And you can see that in this case, oops, okay. Maybe that will make it. Somehow I can't see my own slides because of the, there we go. Okay. So if you think of E1 and E2, you know, just by triangle inequalities and so forth, in this case, for the moment, assume that this is fixed. It's not a distance interval, but a fixed bar. If they are distance intervals, then in fact, this thing will have 5 more dimensions. So I'll have to draw this as a 7-dimensional object. But if these were fixed bars, then I'm drawing here all the possible values that E1 and E2 can take. So you, because of the obvious triangle inequalities and so forth, you have, you know, an upper bound here, and another upper bound here on the maximum length of E1 and E2. And then you have, because of the other triangle inequalities, there is a minimum this length and this. So you can, the zone of possibilities for Z1 and E1 and E2 is this convex region. So what we can show is that, and it doesn't matter, even if these guys were distance intervals, you just have a higher dimensional space, 7-dimensional space, but it's still convex. So now the question is, for what graphs is it the case that you can find these non-edges so that the corresponding, we call Cayley configuration space, is convex? And we were able to show a general theorem, and in particular, for 2 dimensions, for d equals 2, which is that picture that I showed, all of these graphs, these series parallel graphs, have the property that you can find these Cayley parameters, as we call them, these guys, in such a way that the corresponding thing is convex. So now why does this help? Because this is convex, you can use any convex programming technique to sort of traverse this. And then for each one of these values, now you've got values, fixed bars for this. And now this is rigid. And because it's rigid, and it's a simple rigid object, which has a ruler and compass type of realization. So because you can, once you have these 2, these 3, the positions, and then you can find the position of this and find the position of this.
Sorry,
So
Meera,
yeah,
you're saying now it's rigid. Now after what? After you add this
yeah, for a
two.
fixed value. So if I go in here and look at a fixed value for E2 and E1, yeah. So in other words, that's corresponding to actually having fixed these 2 lengths. So as I traverse this, I have different possible values for E2 and E1. And this is a convex region. And for any point in here, that corresponds to a particular value of E2 and E1. And that, if I go and look at that particular value, that gives me a rigid object here. So rigid if these distances were fixed. For the moment, I'm assuming that. Right? So then I can, because it's rigid, then I can find its and because it's such a simple rigid object, I can find its realizations. By realizations, I mean positions of the points that satisfy these constraints very quickly. And so that means that this horrible configuration space, linkage configuration space, can be now traced out in this by just walking along this convex region.
Yeah,
so yeah.
Now it's clear. Yeah, what you meant when we chatted. Yeah, yeah, completely clear. Thank you.
Okay, so and there are multiple solutions for each one of these. There may be finitely many solutions, finitely many. So above this down, this is sort of like what they call a in topology, they call it a branched cover. So this is a covering map. So essentially, you can think of this as on top of this a bunch of pancakes. Each of the pancakes represent one of the possible positions. Let's say one pancake would have this point on the right side of this line, and another pancake might have this point on the left side of this line. And the 2 pancakes would join with each other. They correspond to bifurcations of the position where this guy is directly on this line, right? So essentially, you have all these pancakes sitting on top of here, and that whole mess of pancakes with all the bifurcations and things, that's the actual configuration space of this linkage. So but you can trace that out by just walking this simple convex region. So anyway, we have this very general theorem that when this convex Cayley parameterization exists for a given graph is exactly for these deflattenable graphs. And that happens to be a forbidden minor class, which means a graph that a class of graphs that can be defined by just forbidding certain minors, just like in these series parallel graphs were forbidding K4 minors, so, and not only that, we can actually prove this to even for all, not just Euclidean case, for any polyhedral norm. And the forbidden minors depend, of course, on the norm. So, and this idea of deflattenable graph is its own very interesting theory, and lots of convex programming involved there. So
Sorry,
anyway, we
Meera.
use this idea. So going back to this original problem of, okay, what if you make a free-form deformation of this, and then now you have to go and assert these constraints again. The idea is that we can use this Cayley parameterization stuff to solve for these new positions that after you do the free-form deformation, to solve for the new positions that still satisfy these constraints, and that's
Meera,
usually a very hard problem, but what this is showing here is, you can see the corner sharing triangular structure here. This is showing here is that it's a particular way of solving for these new positions by using the green edges as Cayley parameters, and that we can ensure give you a convex configuration space if you drop all the red edges. So in other words, you drop the red edges, then you have a black graph, and the black graph has our property. It doesn't have the minors that we, K4 minors. Then we add the green as the Cayley parameters, solve, have the convex space there, and then solve for the actual values of the red edges that you want. So this is the very fast method, and this is sort of the underlying, as I said, the slice of the actual Cartesian space looks very bad, but we just use this convex underlying space to explore this. So anyway, we use this. I don't know if you've seen this strand-Beast. This is this humongous thing, and we use this Cayley parameterization idea to completely trace out the the configuration space of this strand-Beast. And I also heard someone talk about the Stonewall's defect. And one of the operations, if you remember, was this using the Stonewall's defect as a way to sort of explore the space. We were able to prove some theorems based on simple number theory on what I call fairy sequences on these triangular lattices that sort of allows us to give a very fast algorithm for talking about the propagation of Stonewall's defects, which are understood to be an important mechanism by which cracks propagate in things like graphene and other such lattice materials. So typically they use finite elements to model this crack propagation starting from, in this case, a Stonewall's defect. So it's a cascade of Stonewall's defects. And basically we just have a, discrete algorithm that sort of given any direction of propagation such as this, has this algorithm that will now generate this as an edge, so to speak, in this new triangulation using a sequence of flips. So that's another sort of discrete simulation of a crack. So this is just from our algorithm. We get these, we can create cracks in any direction you want. So essentially, this is just showing an evolution of this crack, but you give a direction. So in other words, you start out with some lattice direction. So it could be that one, for example. And say, imagine that you're pulling in this direction, this sheet of graphene. We can simulate this, this crack in that direction using a very fast algorithm without using finite elements or anything of that nature. And comparing against MD simulations, doesn't seem to do so badly. So this, if you will, these are all little tiny little particles, so to speak. That's what they do for MD to talk about the generation of the crack when the loading is in a particular direction. So anyway, I've been talking for a long time, and I've told you several things that I do, which I sort of vaguely thought that somebody here may be interested in. But if you're interested in anything, just let me know. Thank you, by the way, for inviting me to talk.
Thank you, Meera.
Yeah.